This next setup here is the derivation of the simple pendulum. All right. So the simple pendulum, when they refer to a point mass pendulum, that's what they're referring to. So this is the derivation of a simple pendulum. Pendulum. Okay. So I'm going to try to draw this as best as I can. Now, this derivation works only for small angles, so I'm exaggerating this angle here. And when they say small angles, they mean, I believe they mean less than 0.2 radians. All right? And 0.2 radians, is that like 10%? I think. About 10 degrees, I should say. So here's an angle theta. Okay? The length L of my pendulum, I'm going to label like that. And so that's my pendulum. Let me go with a different color to draw other things here. So let me go with like that dark color right there. Okay, so I'm going to draw the force of tension on it. So a force diagram. Okay, so I'm going to label this T for the force of tension. And mg, okay, mass, the weight, okay, and I'm going to break this down into its components. So it's going to have one component here. By the way, what's this angle right here? This angle right there. What should that angle be? Okay, that angle should be theta. Very good. Okay. This component here, that component's the important component. That component is mg what? Yeah, mg sine theta. Okay. And the distance that this object is traveling, let me go with a different color here, just so that it doesn't get all confusing. This is going to traverse a distance that we'll call, I'm going to draw this out like that we're going to call S. Okay, and again, this is going to be for really, really small angles. I'm going to go with, back to a different color, go over to the black. Okay, so just like before, where we started off with the sum, with the previous derivation, we said the sum of the forces equals the mass times acceleration. In this derivation, we're going to start with a tangential force. Okay, so that means tangential along the S there. Tangential. And then we're going to set that equal to the mass times the tangential acceleration. Okay, and this tangential force will therefore just be mg sine theta. Now remember, the negative sign means it's a restoring force. It always pulls back towards the middle. Mg sine theta. So this is supposed to be very close to simple harmonic motion. And that's going to equal the mass. Now the distance it's traveling now is this distance s. Okay? So it's tangential acceleration there, remember it was d, it was the second derivative of the position before. Now it's essentially the same thing, the second derivative of the position, but we're just calling the position s now. Okay? Because it's going along that green line. Now, remember, what's the, for position, what's the, as far as position is concerned and angular kinematics, what is the, what phrase do we use? A bridge. What is the bridge between, or what is the bridge equation, I should say? We got V is equal to R omega was the one for velocity. What's the one for position? Remember? Okay, yeah. So S is equal to R theta. But in this case, instead of R, I'm using what? Yeah, I'm going to use L. All right, so S is going to equal L theta. You going to live over there? Oh, here we go. All right. So S is going to equal L theta. Okay. And because the L is constant there, okay, I can make the derivative here, the second derivative, ds dt. Okay. I can pull L out and say that's d theta dt. Okay. And so my equation then becomes this. Okay, it becomes negative mg sine theta. And over on this side, I have ml, with the second derivative of the angle. Okay, so that's the second derivative of the angle. And then I'll rewrite this equation to look like this. Negative g over L sine theta is equal to, again, the second derivative of the angle. Okay? Now, one of the things you have to discuss when you're writing this particular derivation is the small angle approximation. So you will have to say this, small angle approximation. Make sure you include this, and I'll just say that, small angle approximation. Okay? The small angle approximation basically says for really small angles, theta is equal to the sine of theta. All right, so just to make sure we prove it to ourselves, let me hit pause here. Oh, all right, so now that we proved that to ourselves, okay, we can rewrite this equation to look like this. I'm just going to flip it around, and I'm just going to write it like this, d theta dt. Okay. So instead of negative g over L sine theta, I'm going to write what? Yeah, just theta. Okay? Because of our small angle approximation. All right, so remember, the solution to this, we don't have to go over this part again. Okay? So the solution to this is, let's write this out. So the solution to this equation, we already solved this. We already did this part of the proof. So go back and look at your other notes from the first day of simple harmonic motion. We said that the solution would be theta will equal theta max. Okay, this is the maximum angular displacement times the cosine of omega t plus phi. Okay? And remember that from out of this, we also proved that omega would therefore equal the constant in front of there, and that would be omega over the square root of GL. Okay? And since we know that omega by definition is 2 pi over the period, 2 pi radians over the period, then we could set these two equations equal to each other. Okay, and I could say that the period of a pendulum, this is again a simple pendulum, the square root of L over G. Okay, so that's the proof, or that's the derivation for a simple pendulum. All right, don't be surprised if something like that comes up on tests in here or on the AP test.
The whole thing or just the...
Well, I would start with the whole thing. Sometimes they tell you things like set up the equation, but you might as well know the whole thing. All right?
Everything we just signed from before.
Yes. Again, where you want to be careful though is we skipped a step here in the solution. Okay? In this solution, we went from here, we basically went from here to here, and we skipped some steps. Go back to look at your notes from the first day to see how we went from there to there.
All right, yeah, because I was...
Okay. All right. So the next proof is a derivation for the physical pendulum. Okay. So this is the physical pendulum. A physical pendulum is a rigid body that's acting like a pendulum. Okay, yes, we're going to use, actually, yeah. So here's what we're going to do. We're going to have a pivot point like we would expect to have. So that's the pivot. Okay. Whatever this object is, it's going to have some distance d from its center of mass. So I'm going to label this its center of mass. So, and it's going to have some distance mg, or some weight mg. Okay. Now, really important for this, that because it's a physical pendulum, we're not using Newton's first law or Newton's second law that we're normally used to. We're gonna start off with his rotational version of his second law. The sum of the torques is equal to I alpha. Okay, because again, this is a rigid body that's going to be moving back and forth. Okay, in a similar fashion, we're going to have minus mg. Now we're going to have the d part of it, sine theta. Okay, so similar to the regular pendulum. Okay, and that's equal to I. But this part's easy because by definition, the acceleration, the angular acceleration, is the second derivative of the what? It's the second derivative of the what? Of theta. Very good. That's even something you've covered in calculus, right? Okay, good. All right. So we're going to, so that's alpha. So I can replace that with this. Okay. And again, I'm going to use a small angle approximation where I'm going to say theta is pretty close to sine theta.
Okay, so the other one was a theoretical pendulum?
The other one was a point mass pendulum. Okay. It's called a simple pendulum. All right. So then I'm going to just rewrite this as minus mg d theta is equal to I second derivative. Okay. Like that. Okay. And then, yeah, go ahead.
I'm just on the second step where negative m.
Thank you for asking that, by the way. All right. So, let's just, collect some terms here. So this is going to be negative mgd over I. Okay, I'm just going to put theta out here just to emphasize the fact that that's what we're taking the derivative of here. Okay. All right. Now, so remember, just like before, the solution to this, okay, the solution is once again theta is equal to theta max. Remember, theta max is going to be the maximum angular displacement cosine omega t plus phi. Okay, and in this case, omega is going to equal the square root of mgd over I. But because we also said that omega is equal to 2 pi over the period, then the period will equal 2 pi times the square root of I over mgd. And really important here, when I was doing these problems, I was made very well aware of the fact that this d, okay, that's the distance from pivot, from pivot to center of mass. Okay. Now, center of mass is a topic in calculus, right? So you guys have been solving for that? In AB? Not in AB? You guys do? Have you guys done in BC?
Yeah.
Yeah. Okay. And, okay. So, like, for like a solid cone, that sort of stuff? Isn't it like 1/3? Two-dimensional? Okay. All right. I'm going to, all right. So this is an example. Hopefully I have the pen here. Okay. So this is going to be an example of a physical pendulum. Okay. This physical pendulum, okay, listen up. This physical pendulum is going to be made of a rod. Okay. Mr. Claren can't draw straight lines, apparently. That's a rod. Okay. Connected to a solid sphere. And I can't draw a solid sphere either. So, solid sphere. Okay. All right. The rod's going to have a mass, or I'm sorry, a length L. Let's label the rod's mass as m sub r. The sphere is going to have a radius of, let's make it big R, and have a mass of m sub s for sphere. Okay? So the first question is going to be, what is the rotational inertia relative to the pivot point? So number one, what is inertia relative to pivot? Okay. So remember, our total inertia in this case is going to be made out of what things? Okay, the rod and the sphere. And also, we also have to apply what else? Because the rod's, yeah.
The parallel axis.
Parallel axis theorem. Okay. So, we're going to have to add the rotational inertia of the sphere, the rotational inertia of the rod, okay, plus the rotational inertia of the sphere's center of mass, okay, which is essentially the parallel axis theorem, okay? So we're applying the parallel axis theorem here.
So I sphere is just going to be mr squared.
Yes. Yes.
All right.
Okay. So, but including the radius too. The parallel axis theorem.
Okay.
Okay. So look at this really carefully because I kind of took some shortcuts when I was doing this and missed a couple things. Okay, so let's look at, so first of all, the rotational inertia of the sphere is going to be what? What's the rotational inertia of the sphere? 2/5.
R squared.
Yeah, let's use the symbols I have here. So ms for the sphere, I'm using capital R squared. Okay. What about for the rod? It's at its endpoint. Anyone remember that?
1/4 ml squared.
I think it's at 1/3. Okay. So mass of the rod. Okay, and let's use L squared. Okay. Now this is the part where we're including the parallel axis theorem. Okay. The parallel axis theorem, remember, is just md squared. But the important thing is the d is the distance to the center of mass of that object. So here's the sphere. We're going to apply the mass from the pivot of the masses, okay, both mr and ms, right? So mr plus ms, okay, and at that distance, L plus R squared. Okay? Yeah.
Why is the L number one? Why is the L over 2?
Because of the middle one, because this is, that's, remember we proved that that's what it would be at the end? Okay, but it's not the center, because it's not the center of mass, it's the entire value of it. Okay? All right. Then we've got, question number 2, but that actually will come up, okay? Okay, I didn't label that. Question number 1, question number 2, okay? What is the distance? The distance between the pivot and the center of mass. Okay. So we're going to apply that equation. So let's put center of mass of entire pendulum. Okay, so that's where we apply this equation, this center of mass equation. All right, so I wanted to throw this in when it was more appropriate. This is an appropriate time. So that equation, remember, this is from your equation sheet. It says you take the sum of all the masses and their distance from a particular point, in this case relative to the pivot, and divide that by just the masses. Okay? So I've got the mass of the rod, okay? The mass of the rod, so M sub R, but for this R, I'm going to use the distance to the pivot point. So for the rod, what am I gonna put for its R? Good, L over 2. Okay? So that's what I think what Justin was referring to earlier. And then for the sphere, I'm going to use the mass of the sphere and then multiply it times its distance to the pivot point, which is going to be what? What? L plus R. Okay. And then I'm just going to divide that by all the masses. So M sub R plus M sub S. Okay. And remember, this is all relative. Okay. Make sure you make a note of this. Relative to pivot. Okay. So then number 3, when we calculate out the period, the reason we did all this is when we calculate out the period, remember we're going to use the physical pendulum period equation. I over mgd. What am I going to use for this I here?
The sum of the inertia.
Okay, the I total that we calculated out earlier. And what am I going to use for this D here? Yes, I'm going to use for that D, I'm going to use the R center of mass. Okay? All right, so that's an example of how you would do. So right here, in this equation, we need to get rid of, here, let me use a different color here. So have this out. We need to get rid of the mass of the rod right there. Okay? Because, see, in the parallel axis theorem, it's the center of mass of that object that's away from the pivot point. So this part right here, this part should just be, okay, if I need to rewrite it again, it's just the mass of the sphere times the distance away it is from the pivot point. So L plus R squared. Okay? Oh, I'm fixing it though, so it's helping out. Okay.
You never did.